So, we again will start discussing about high level synthesis. In the last class we have talked about profiling and all those things, but some of those things I would like to repeat once again today, because I felt that it was not very clearly explained in the last class. So, if you just to put you in perspective, you can see that this was the control and this was the flow FSMD of the problem, that is a square root approximation algorithm, okay, using this. So, and we came to when we are trying to do the profiling, we came to this. Now, what I would like to mention is that these points, I am making a matrix, and in the matrix you can see that these are all the variables, right? These are all the variables. Now, I put a cross on the particular element depending on the liveness of the variables. For example, I find that at state S3 x is live, say here x is live here. Before that x was never live, right? X becomes live here and x remains live up to this, all right. X remains live here also in S4, and also x is being used in S6. Therefore, all through this x is live. Okay. Similarly, here say S4, in state S4 I am having x live, I am having T3 live. Why? T3 started here in from state S3 and T3 is being used up to this S4. So, that is also live. What about T4? T4 was made live at S3 and it was written after S3 and is live in S4, right, because T3 is being used here. You can see that. Therefore, this one is live. This S4 has got 3 variables which are live. So, so you can see that these 3 variables are live in state S4. Okay. And similarly, in S5 you can see that of course, variable x is live because it was initiated in S3. It is also available in S4, it is live. In S5 it is live because it is being used in S6. Therefore, it must be live here also. Okay. And what about T4? T4 was born here, just after this. So, T4 is live here, is being used here. Therefore, it must be live for all these states. Okay. In that way, we make the liveness matrix here. Similarly, we are making this operation usage matrix in which steps they are being used. Okay. So, that is how in the last class we were hesitant to explain this. It is not on the variable usage, it should be rather I should say it should be variable liveness. Okay. It is variable liveness. All right. So, next we move to so, based on that was the profiling, and we will be doing different steps like storage sharing, functional unit sharing, that we discussed in the last class. So, and we also saw this, that how we can gain by combining registers depending on the liveness of the registers. This was discussed and I think that was clear. Just to repeat, you can see that since A and C are not being used in the same step, so they can be combined to be one register, and thereby I save on the number of registers here, and here x and y being combined into 1, I can save in the number of selectors here. Okay. So, that is clear. Now, when we talked about this compatibility graph, there were some confusions. So, let us work it out once again today. So, for the compatibility graph part, first we have to identify the incompatibilities. Okay. So, I have got my variables. My objective of using the compatibility graph now is for looking at the variable margin, how I can combine the variables. And once that is clear, the same thing will apply for functional unit margin and others. So, I can see I have got variables okay, A, B, T1, T2, X, Y, T4, T3, T5, T6, T7. Now, first I connect the incompatibility edges. Just the incompatibility edges are the edges which are occurring at the same time or are sharing the same resource. So, you see here A and B are occurring at the same time. So, I add this edge to it. Similarly, for T1, T2, they are being used at the same step. So, they are incompatible. What about X and Y? X and Y are being used in the same step, they are incompatible. X and T4, Y, are they incompatible? X and T4, here X is being used and I need to keep the value of X. Here X is live from this point, and when X is being shifted, T4 is also being written, because the shifting is being done in the same clock. Similarly, X and T3 are incompatible. So, I first mark the incompatibility edges. So, I get only the dotted edges. I have not drawn any compatibility edges till now. Now, anything, the complement of the incompatibility graph should be the complement of the incompatibility graph would be the compatibility graph. But here I am connecting the nodes which are somehow, I just want to put in some sort of a precedence of merging among these. I am connecting these based on which are the nodes that are using the same resource. For a second, let us concentrate on this part only, and let us look at what are the functional units that I am using. Okay. Let us look at the functional units. So, I have an absolute computation, all right, absolute computation coming at this stage, okay, and its input is, say, actually it is coming here. So, its input is A and output is absolute value of A. Okay. I am using another one which is B, all right. Now, here I have got a max operation, and what are the inputs of max? T1 and T2, and output of max is X. I have got a mean operation here. That mean operation also has got T1 and T2. and I am getting y. Okay. Now, so here you see that max and mean are sharing the same inputs. Now, here I have got a shifter and that shifter has got input x and output is T3. I have got another shifter whose input is y and output is T4. What else is left? Plus and minus. Now, this minus has got x and T3, right, and output is T5. Plus has got T4, T5, and the output is T6. Again I use the max here, right. Here again the max is there. So, I come back to this max. Now, at this max again I am needing the inputs are T6 and x. So, here I have got T6, I am drawing it with a different color or make it a little elongated, T6 and x. Therefore, you see T2 and x, T1 and T6 are using the same resource here. Now looking at this usage pattern, let us try to see, mark these edges where the resources are being used. For example, you see T1 and T6. What is happening to T1 and T6? You look at this T1 and T6, these two variables T1 and T6, these two variables are being used in the same max. T2 and x are using the same max, right. So, here you see, and what are they sharing? They are sharing as the input. They are sharing this component, they are inputs to the same component. Therefore, T1 and T6, they have got one input common, no output common. This operator, okay. So, because when next time this max is coming, then the output is T7. So, that is a different output. Okay. Now, let us have another look, x and T7. What is our take on that? X and T7. X and T7, let us come here. X is using the shifter. Where is T7? Yeah, sorry. This max, the output was T7. The last max, output was T7. So, X and T7 are using the same operator as the output. Okay. Therefore, if I can merge them, that will be the same. I can, since both of them are coming from the same operator as the output in two different control steps, I can try to merge them. There is a possibility of merging. So, this merging possibilities are being shown here. So, that is 0 1. I hope it is clear. Now, let us once again try T6 and T2. What happened? T6 and T2. Let us look at this again on the paper. T6. Where is T6? T6 is here, and where else is T6? Max. T6 and T2. Yes. T6 and T2 are sharing the input of the same max. Therefore, they are one sharing. I can, because see this max is commutative operation. So, I can very well make the left input the right input, that is not an issue here. So, therefore, that is also 1 0. Okay. So, that is how we make this compatibility graph where we mark the incompatibilities and then give the precedence of the or the possibilities of merging with 1 0, this sort of thing. Now, last class we were talking about that if I merge say this one, I could have merged something else also. This T3, T4, T5, T3, T5, T6, they are compatible. Similarly, but by merging them, what do I gain? I gain in one source point and one destination point, you see. So, I can merge two variables here. Here, if I had merged only these two, T2 and X, I would have gained in 1. If I had gained in, if I had merged T2, X and T7, that would have yielded me the same result, that 1, 1, right. So, I had a choice of merging these 3 and this one or these 3. Now, these sort of decision making will be coming up at every point of our design algorithm, and there are different ways of different heuristics that are adopted, different heuristic measures that are adopted to decide on which one to be adopted, which one I should go ahead. Those of you who are aware of the algorithms, now of course, I can go by some greedy method, or I can go by some branch and bound, or I can take some linear programming approach. Different approaches can be done to find out what will be optimum for me. So, here we have taken this T3, T5, T6 to be merged. Now, once that is merged, what else can come with this? We saw this in the last class. This one can come T1 X T7, T1 X and T7, that can also be merged, because that will give me a benefit of again 1 1, all right, 1 1, the same thing. So, I merge them. As soon as I merge them, then T4 became incompatible with this cluster, Y, which was otherwise compatible with X, has now become incompatible with this cluster, right. Can you see that? All right. And T2, which was otherwise compatible with X, has now become incompatible with this cluster, because T2 was incompatible with T1 and I have brought T1 in this cluster. Okay. So, now I am left with this. Now, what can I do? I cannot bring it in here, but A and B I can bring in. T2 is not incompatible with this. So, I can take T2. So, I can take T2 in the, what is happening?
In this case,
yes.
So, the Y is Y now incompatible, because Y was compatible with X earlier, and so was it with T2 and T7. Those X's are not there.
X and Y should be incompatible in the second one. So, in the first one also it is incompatible.
Yes.
What did you say? What?
In the first figure, sir, step A, Y and X are incompatible, sir, and they're shown to be compatible in the second figure.
In the third one again they are.
That was a mistake, might be. This should be a dotted line. Yeah, that was if X and Y, let us see, X and Y are incompatible or compatible. They were incompatible, right, because they were in the same step. So, X, so here is a mistake. This one is, this should be a dotted line, okay, as is being shown here, all right. So, now what happened to this? Let us look at this. Therefore, now what is happening with this? So, now I will further try to continue with this merging. Yeah. So, now I have got this. So, from there I came to this. Now, the third one is, once these are done, then I can merge. Which one can I put in over here? I can merge T2 and Y, these two can be merged together, and T2 and Y can very well come to this cluster because they are compatible with this. So, I can have this sort of a clustering. Okay. Now, A and B are, I mean, they are not at all in any conflict with this. So, it can go in any cluster. So, I could have merged A here and B here and A here. I could have done it in the other way also. Therefore, I have now, so given all those, so many, how many variables I had? I had A, B and X, Y, 4 and T1 to T7. So many 11 variables. Now, I have been able to merge them into 3 registers. T4 does not go with anything else. Therefore, T4 will be in one register R3 and A T1 X T7 goes in R1 and B T2 Y T3 T5 T6 goes in R2. Okay. So, now I have got 3 registers. So, that is how we have been able to merge the variables and we get 3 registers. So, that is how we carry out, we are now trying to do the optimization at every step. Okay. So, now how would my data path look like? My data path will look like this, that now I have got 3 registers and I have got all the explicit units. Now, one thing I should have mentioned here, that when I created this precedence graph, here I also looked at, I actually looked at the library of functional units that are at my disposal. See, whenever I am doing it, I am given specification graph. I have got a specification graph, and on the other hand, I have got a library of available functional units. Here, when I made this graph, I have assumed that there is an adder, there is a subtractor, there are shifters, there are max, mean and absolute comparators, absolute computations. Also, I have assumed that there might be some ALU which actually takes care of the plus, minus, max, mean can be put in here, that was another possibility, and abs, and shifter was something else separate. Now, this shifter we actually handle in a different way, because I can actually have a shifter or I can do shifting on the fly, right, by just doing some, adding some control steps. I mean, I do not have to pay any, I may avoid paying any hardware cost for that. So, given this, here we are showing that we are not economizing on my functional units or the library, I am not economizing on them, I am using them explicitly. And so, if I do that, I have got A, mod of B, mean, max, all these things are here, 2 shifters, and this is the data path, and these are the registers which hold these variables, fine. Next, what do I gain by functional unit sharing? I again come with an example here, the same example, say I have got A plus B going to X and C minus D going to Y, and here I find that A and B, C and D are coming to 2 different functional units, but very well I can merge them into one ALU which can do both addition and subtraction, and assume, let us assume that the cost of the adder plus the cost of the subtractor is less than the cost of the ALU. If that be so, then it is prudent to have this, and consequently what are we gaining? So, not only this, we are gaining, we are adding 2 selectors, okay, because now I need to include the selectors. So, the cost of this plus the cost of the selectors should be less than these 2 addition. all right, and here I can send it to x and y, here I don't need anything. So, that is what how I can gain by sharing functional unit. Now, this is a simple case. If I come to the operation merging for a square root algorithm, now what are my operators? My operators were, as was shown here, all these were the operators 1, 2, 3, 4, 5, 6, 7, 8. Now, I have kept out the shifters, all right. The reason I have already told. So, I have got 6 keeping out the shifters, because the shifters I can handle separately. So, here you can see again in the same way you confirm that A and B are incompatible. I am sorry, not the variable A and B. I am saying this operation mod A and operation mod B are incompatible. Why? Because they are taking place in the same step. Okay. Mod A and max are not taking place at the same step. Now, let us look at, I have marked it 1 1. Why? Let us see what happens to this mod A. Mod A goes to T1, right. Where is T1 located? T1 is located in R1. So, T1 can be synonymously attributed the value R1, the name R1, right. T1 has been put in R1. And what happened to max? Max is taking T1 and T2. So, max is taking T1 and taking x. Now, you see, so T1 max is sharing T1, that is R1 with mod of A, and also as an output it is sharing x with mod of A with with R1. So, R1 is being shared both as a destination also as a source. So, I have marked it 1 1. Okay. Let us take another example, plus and minus. What happened to them? Plus, where is plus? Plus is here, all right. So, this plus T6 assigned T4 plus T5, I can now write as, if I just go by RTL, register transfer logic, what would it be? T6 means which one? Can I write this? T6, where is T6? R2. So, R2 is getting T4 plus T5. Where is T4? T4 is R3 and T5 is R2. So, R3 plus R2. And what happened to the minus? Where is minus here? Minus is T5, T5 is R2 and what is being subtracted? X, which is R1 minus T3. Where is T3? R2. Now, looking here, we can see that one destination is shared, one source is shared, right. Therefore, it is 1 1. In that way, we can make this graph clear. Now, once we make this graph, now we go ahead by combining, and there also we look at the gain. I could have merged these two, I could have merged these two, because they are giving me benefit of 2. Here I am getting benefit of 2. Here max and minus, let's work it out again just to make the thing clear. What is happening to max? Max is taking T1, T2 and going to x. T1 is where? R1, R1 and T2 is where? R2, and these two are being maxed and going to max, it is going to x, x means R1, all right. Max is again here, there is again max here, T6 and x. T6 is R2, it could be R2. I have already merged that. So, and x is R1. So, you see, for both the operations, that is the beauty of the merging, variable merging that I have done earlier, that now these two registers are containing all the variables for the two instances. So, I do not need to do anything else, and where is that going to T7, and T7 is R1. So, now you see what am I gaining here? Are both of them going to R1? T7 and what is T5? Sorry, if I take this T5, sorry, max and difference, sorry, I have to take the difference, I am sorry. So, difference is x and T3, x that means R1 and T3 is R2. So, I take a subtraction of them and store it in T5 is R2. So, here we are sharing two sources, the destinations are different, but the sources are the same. Therefore, it has been marked as 2 0, clear? All right. Now, so we go ahead with the merging. So, I first merge these two, I could have merged these two as well. Next, I go on doing this. So, these two were merged, then I merge min with this, max cannot come with this because of incompatibility. Now, other things can come in, A and max has been put in because they are compatible. So, I have merged these two, then this, and A and max has been merged, and all these B can easily come to this cluster, B can come, therefore, I have got this as the final graph partition, clear. So, I have got now, therefore, how many besides the shifter, what else do I need? I need two operators, two functional units, right. So, that is how I have reduced it, and these two are incompatible, might be they are active at the same step or there are other usage patterns. So, ultimately I come to this abs and max, one abs, and abs mean plus minus, that is another one. So, I have put in some selectors, and shifts I have kept separately. Okay. Next, quickly let us look at still another thing that we need to optimize in high level synthesis are the interconnects. Those of you who have worked with such design, you see how troublesome the bunch of wires are. I mean, and when you come to the PCBs and all those, the interconnects play a very important role in terms of real estate as well as for other purposes, other benefits. So, here we are showing the interconnect points A, B, C, D, E, F, G, H, each are the in points, and the output points are I, J, K, L. So, I write them down, okay, I, J, K, L, and here this M, N. So, I write them down, and again I look at the connection usage table, just as we had done earlier. Now, in the same way, we can merge the connections into buses. Now, what will be our compatibility now? The compatibility is that whenever, now here I have not put any compatibility, means whenever two connections are active at the same time, I cannot merge them. Two distinct connections, say for example, A is active here, look at this table, A is active here and C is active in other states which are disjoint, right. So, A and C are compatible. What about A and B? A and B should also have been compatible, okay, but I mean C and D are they coming at the same control step? No, in two different states. So, based on that I can draw this graph, and in the same way I can merge the graph and get buses, all right. All the interconnects I connect, suppose I do this, and I therefore, I get the interconnects A, C, D, E, H, this should be capital, I am sorry. So, I will get 4 buses. So, in the same way, I am not spending too much time on that, you can yourself do the exercise and see that ultimately the design which was gradually was being refined and came to this scenario. Now, so after merging the buses, we could come to this, where I have got only 4 buses, 4 functional units. Now, it is now your decision, you could have merged these two also. You could have merged these two also, but now I have got a much neater design, not only neater design, but much more cost effective and cheaper design, both in terms of real estate as well as cost. Okay. So, similarly, last thing that we would like to do is merging the registers into register files. Now, I have got these registers R1, R2, R3. Now, you know a register file. Register file is a box of registers, all right. So, when I can access the register file, I access the register file at a time. So, can we merge these further? You see, my R1 is A T1 X T7, all these variables are there. Now, I look at what are the, if you just apply your mind, you will see that I actually do not need 3 registers, because they are now, till now I have not looked at which clock cycle they are reading or writing. Here what happens is, at the first clock cycle in state S0, this one is being written, R1 is being written into, because A is there. So, R1 is being written into, and at the same clock, I mean here S1, in state S1, I am reading R1, I am reading R1 here. Okay. Now, in that way I just plot this, that this is being at, so let us take R2, at state S0, R2 has got B. So, that is being read, R2, B is being read and B is in R2, written, B is being written, and here at the next clock B is being read, all right. Similarly, for the state S1, at this point R1, state S1 here, R1 is being read, and all this are being done. As I plot in this way, I find that R1 and R3 are compatible, because nowhere where R1 is being accessed, R3 is being accessed, but that is not the case with R2. R3 is being accessed with R2. Here you see, R3 is being accessed with R2, but R1, wherever R3 is being accessed, R1 is not being accessed, right.
I think S3 is wrong, sir, because R2 is not been written to in S3.
No, it is the same clock. S3, in S3, I am taking X, and X is in R1, right, and shifting it, and Y is in R2, and Y is being shifted. Therefore, both of them are being active, but R1 and R3 has got no conflict. They are being accessed at mutually exclusive times. Therefore, they can be merged and we can get a better result. So, I merge them in R1, R3 in a register file, and I have got R2 here. So, my design becomes much more effective. Okay. So, I stop here this part. So, we have, what have we done here? We have seen that we start with a FSMD or some specification and make an FSMD out of it, and from there how we can do profiling, and step by step we can go for optimization. Actually, for larger circuits these things are done by software, but such optimizations, but you need to know what is the basic, how the, say for example, you have to design an embedded system in which you have to make a small ASIC, very simple ASIC, and you do not have any access to any tool, then this is the approach by which you should go about. Okay.